exists because it is a singular matrix for this matrix. Since it is a singular matrix, the inverse of it does not exist. And there are also other examples where inverse of matrices do not exist. For instance, we have a linear function like this, but this matrix itself is a rectangular matrix. So the inverse may also not exist. In this case, we have to introduce a generalized inverse of a matrix. And the definition of generalized inverse matrix is something like this. For a given matrix A, if there exists n satisfy A times n times A equals to A, then n is called a generalized inverse of a matrix. And it is mathematically denoted like this. And this is called the generalized inverse matrix of A. And if you are trying to solve this kind of problem, you may find that n is not unique. We may have infinite number of n satisfy this kind of condition. And among this infinite number of n, which is the best n? For instance, if there is a linear equation like this, we may find x which satisfies this kind of condition, which means to minimize the error in this equation. And in this case, we can find a unique n. And the unique n is called a Merpenrose generalized inverse. Also, it is called the pseudo-inverse of a matrix. The condition it must satisfy is not only this condition. If you use only this condition, as I said, it will have infinite number of n's. Apart from this condition, we may have the other condition. For instance, we have m times a equals to m. This is another condition with the requirement structure. And also it have a times m and n times a are Hermitian symmetrical. In real matrices, we say that they are symmetrical, as in our body. For compact matrix, for real matrix, we will have something like this. However, for complex matrices, we may have something like this. This means that we take the transpose of the matrix and then take the complex conjugate we will have. Well, we may have this kind of equation. This kind of property is called Hermitian symmetrical. So if all these three conditions are satisfied, the matrix M will be unique. And we call it a Merpenrose generalized inverse or pseudo-inverse of matrix A. And the mathematical form is something like this. So now the question is, how can we find the pseudo-inverse of the matrix? In Matlab, to find the pseudo-inverse matrix might be quite simple. We just put a p there, means pseudo. Then we can find the pseudo-inverse of the matrix. And in the numerical computation, sometimes we need to put a precision requirement or error tolerance epsilon there. Now let's go back to this example again, because this matrix itself is a singular matrix. The inverse of this matrix does not exist, we cannot expect to have a matrix with satisfied AE equals to identity. There isn't such a B exists. So what we need to do is to find the pseudo-inverse. So we can input A matrix in first and then take the pseudo-inverse to get matrix B, and then we can multiply AE together and see what happens. So this is the pseudo-inverse of matrix A. Let's go back to this command again. We say that if we want to take the inverse of A, we will get a warning message like this, and the number in the inverse will 10 is quite large, 10 to the 14th of the power. But if we want to get the pseudo-inverse, we can have balanced results like this. We may not get very large results for this. And if we multiply A and B together, what we will get is something like this. If we did the inverse, we will get identity matrix. But if we want to get the pseudo-inverse, we will get something like this. It is no longer an identity matrix. But it does minimize the error in the linear equation. AX minus B minimize the error. So this one is unique. It is kind of inverse. It's not the real inverse, but the pseudo-inverse. If we check the conditions, it may not be satisfied at xb equals to I. It will not satisfy. But if we want to check the three conditions, we may say that they are all satisfied. For instance, A times B times A minus A, and then we can take the norm of it. We may see that the error would be very small. So if we can check the three conditions in this way, we will find that all the three conditions are satisfied. So this is the pseudo-inverse of the matrix. And I shall use the pseudo-inverse later on in this course. Now let's consider how can we find the pseudo-inverse for a rectangular matrix. Before we're doing that, before we try to find the pseudo-inverse of that, we can find the rank of matrix A. Since A has 3 rows and 6 columns, if we use a command, 5 columns, if we use a command like this, we will find that the rank of the matrix is 2 instead of 3. So it is not only a rectangular matrix, but also not a full rank matrix. For this kind of matrix, how can we find the pseudo-inverse of it? We can use the same command. We do not have to check A again. We use this command to find the pseudo-inverse of it. And so we can finally find the pseudo-inverse matrix A in this way. A is 3 by 5 matrix, and the pseudo-inverse of it is 5 by 3 matrix. And if we take pseudo-inverse to B matrix, we will get matrix C, and you may see that A minus C could be very small. This means that the pseudo-inverse of A is denoted like this. If we take another pseudo-inverse again, we will get A back. So this is the evaluation of pseudo-inverse. And it should be noted that PINV function can only be used for double precision matrices, not for symbolic matrices.